Hi, this is EJ again. Welcome to the third lecture in the course Advanced Statistics. Last week we discussed inference in cases of one sample, paired data and two independent samples, where the response variable was continuous and mostly normally distributed. Today we will look at similar situations, but with a response that is binary. That is, it has only two possible outcomes. For example, students pass an exam or not. In such a situation, we may be interested in the pass proportion for a given student population, or we may compare pass proportions for two populations. The lecture will be divided into two parts. The first is on the case of one proportion. On page 7 of the study guide, it is indicated as situation 10. We will see how to derive a confidence interval for that one population proportion based on the sample proportion, and how to do a test about it. The binomial test is an exact test. The confidence interval will be approximate. The same holds for the case where we compare two proportions, situation 11. We will see how to test if a proportion is the same in two populations, and we will derive an approximate confidence interval for the difference between the two. So again, an exact test and an approximate confidence interval. The exact test is called the Fisher exact test. Let me first give two examples of the case of one population proportion or success probability. The first is from an observational study. We have a physical animal population, and some animals in that population are infected. There is an unknown proportion of animals infected, and we call that proportion pi. That is a Greek letter P for probability or proportion. We want to know this proportion. That is the parameter of interest. What do? We take a random sample of animals of size n, for example 100. Each animal is either infected, a success, or not infected, a failure. We could count y, the number of successes in the sample, as a summary. Second example, it's more experiment-like. We want to draw a conclusion about the germination probability of a certain seed, from some flower. In a bed of a particular soil type, 20 seeds are planted, and we regard these seeds as a random sample from a hypothetical population of seeds planted in that type of soil. The proportion of germinating seeds in the population is the same as the probability that a randomly picked seed germinates in that type of soil. Let's have a look at the probability distribution of a binary variable first. We know what a normal distribution looks like. Here we have an example of a normal distribution with mean 10 and standard deviation 2. So that is an example of a continuous variable. What if we have only two possible outcomes? Well, then it might look like this. Let's say that 1 means an animal is infected, and that 0 means an animal is not infected. As you can see, the probability of 0 is 0.8 and the probability of 1 is 0.2. And if we call the outcome 1 for infected animals and 0 for non-infected animals, then if the population proportion of infected animals is 0.2, then this probability must also be 0.2 and the other way around. So in this case, the probability that x is 0 is 0.8, the probability that x is 1 is 0.2, and the mean of x is 0.2. And you can calculate it as 0.8 times 0 plus 0.2 times 1. So what we see from this is that our one sample situation of week 1, where we looked at the mean of a continuous variable, is in a way the same as the case that we're now considering. Yet we look still at the mean of a variable in the population, but that is the same, as we will see, as the proportion of successes. Yeah, and you could say that this case of binary data is a case of the most non-normal distribution. All probability mass is on the outside of the distribution. Well, let's have a look how to do inference about population proportion. Yeah, we'll look again at the example 1 at the infected animals. So pi, as we already mentioned, is the population proportion of infected animals. It's also the probability that an animal is infected if you pick it randomly. Thirdly, it is the population mean of x if we define x as 1 for infected animals and x is 0 for non-infected animals. And it appears that the standard deviation can also be calculated, square root of pi times 1 minus pi. Well, how to estimate pi? I think if I gave you a numeric example, you would find it easy. Maybe if you do not get this example, it might be difficult. How to estimate pi? Well, as you will see, the answer is in fact easy. Well, let's first define y, the sum of x's, and that is the same as the number of sample successes out of n. So we have n animals in our sample, y are infected. So what would be our estimate for the proportion in the population? That will naturally be y divided by n. So the sample proportion is the estimator for the population proportion of infected animals. Yeah, so we have again the same elements, you could say, at the parameter of interest pi and the estimator pi hat defined by y divided by n. That is the sample proportion. Pi hat is y divided by n. Yeah, so for example, when n is 60 and we have 11 infected animals, then the estimate for pi would be pi hat is 11 over 60 is 0.183. Well, to be able to do inference about pi, we need to know something about what we can expect for a given pi. So and then in terms of the distribution of y. Well, the distribution of pi hat, which is y divided by n, follows from the distribution of y. Well, statistical theory, and you can read about this in chapter 4 of the book of Ott and Longenecker. Yeah, if pi and n are known, we can actually calculate for each possible outcome of y what its probability is. Yeah, and well, this is such an important distribution that it has given its own, it has received its own name. If pi and n are known and y is the number of sample successes, yeah, and we draw n times independently and each time with the same probability pi of success, then y has a binomial distribution with parameters n, the sample size, and pi, the success probability. And we will use this distribution in the binomial test. A few standard characteristics. What is the average value that we can expect for y? Mu y or EY, it's n times pi. Yeah, so if half of the students in general pass an exam, and you look at a sample of 100 students, then you expect 50 to pass and 50 to fail. The variance is n times pi times 1 minus pi. So here's a thing in which this situation 10, as I sometimes call it, differs from the case with a continuous variable. In a continuous variable, the mean and the standard deviation are separate, but here they are related. So the mu of y is n times pi, and the variance is n pi times 1 minus pi. So if we know pi and n, then we can calculate both. The standard deviation is then the square root. Well, here's an example. For n is 100 and the success probability pi is 0.4. PQRS calls this thing p. If we have 100 sample size of 100 and a success probability of 0.4, then we could expect 40 successes. But by chance, this value might be different. It may be 39, 38, 37, and it may be as low as almost as 25, and it may be as high as 55. So, and in this case, the mean of y is 40, the variance is 24, and the standard deviation is 4.9. And actually we shall see that we can approximate the probabilities that we find with the binomial distribution also with a normal distribution. As you can see, the form of this distribution looks is similar to a normal distribution, except that intermediate outcomes are not possible in the binomial distribution. Well, let's have a look at the normal approximation. That was very important in the past, especially for larger numbers. It was very handy to use a normal approximation. Well, if y has a binomial distribution with parameters n and pi, then approximately y has a normal distribution with this mean and this standard deviation. And pi hat, which is y divided by n, has the same distribution, except we divide mean and standard deviation by n, and we get the following expression. The approximation is used for determining a confidence interval, and for that case we use the standard error of pi hat. That is an important formula. The standard error of pi hat is square root of pi hat times 1 minus pi hat divided by square root n. And here you see the distribution, the approximate distribution of pi hat if pi is 0.4 and n is 100. So if n is 100 and pi is 0.4, you would expect pi hat to be on average 0.4, but it may be as low as 0.25 and it may be as high as 0.55. Well, here we will see how well the distribution of y and its approximation are similar. Let me go one by one. We have y has a binomial distribution, 100 and 0.4. This is the distribution, so values between 25 and 55. Approximately, y has this normal distribution with mean 40 and standard deviation 4.89. And if you use that, you will see that it has indeed the same range, same form, except of course the intermediate values are filled here. Also note that this is called a PDF, a probability density function, and then the probabilities are given by areas, area under the curve, and here it's the probability mass function, and here the probabilities are given by the length of each of all these bars. So the sum of all these bars is 1, and here the area under the curve is 1 as the total probability. And finally, for pi hat, you will see exactly the same form, except the values on the value axis have now been divided by 100, so we get 0.55. And you see 25, 25, 0.25, 55, 55, 0.55. Yeah, so this normal approximation works well for as long as we have reasonably high values for n. Well, in fact, it's about n times pi, as we will see. Example 2. Yeah, we will now use the emergence data on 20 seeds, and now we suppose we have 20 seeds and 8 emerged. So n is 20 and y is 8. And now we wonder, what could pi be? Yeah, so note, up till now we have been talking about the case that we would know pi, and what can we expect for y, and what can we expect for pi hat. But now we will go the other way around. Given n and y, what could pi be? Well, that is this different route is called inference. In the other one, the one we have done so far, is deduction. So we asked the question, which value might unknown pi have? Could pi be 0.1? Well, if we ask that question, then we can be much more specific, because we know that if pi is 0.1, then y has the binomial distribution with n is 20 and pi is 0.1. This binomial distribution is given here. And we see possible outcomes: 0, 1, 2, 3, 4, 5, 6, 7, 8. 8 is somewhere here. And as you can see, the probability that you will find 8 or more is actually only 0.0005. Yeah, so the question, could pi be 0.1? Answer, no. Well, of course, it is possible. It's not impossible, but it's very unlikely. So we reject that case. So the null hypothesis pi is 0.1 should be rejected. And that's actually a little bit how the binomial test works. Yeah, if pi would be 0.1, the probability y larger or equal 8 is very small, so it's unlikely that pi is 0.1. Could pi be 0.4? Well, in that case, y would have a binomial distribution with n is 20 and pi is 0.4. And then we would actually expect a value of 8. Yeah, so 8 has the largest probability. It's also the expected value. So if pi is 0.4, then 8 is very well possible as outcome. So 0.4 is a possible value for pi. And in this case, it's even our best guess. Note, yeah, the reasoning is always sort of upside down in inference. Yeah, so the question, can pi be 0.1? What we do is we say, well, suppose pi is 0.1, could we find y is 8? So we turn the question around. For a given value of the parameter, could we find this outcome? And then we can use our theoretical knowledge and come up with an answer. Well, and if we could find y is 8 with reasonable probability, then we say, oh, pi may be 0.1. But in this case, that was not so. Secondly, yeah, we used here the example of pi as 0.4. We found that pi may be 0.4, but that does not exclude other values. If we would try this for pi as 0.3 or 0.48, we would also conclude that 8 is a possible outcome. So 0.3 and 0.48 are also possible outcomes for pi, or possible values for pi. Yeah, so that it's good to be aware of that the fact that pi can be 0.4 does not mean that it is 0.4. Then we are now ready to summarize all elements for the one sample, one proportion situation. The data is one random sample and observations with binary outcomes, 1 or 0, yes or no, success or failure. The model is that for all these outcomes, the probability of success is the same and that the observations are independent. The parameter of interest is the population proportion of successes, or the success probability in an experiment, and we indicate it by the Greek letter pi. The estimator, which gives us the method of estimation, is given by the sample proportion of successes, y divided by n, y being the number of successes in the sample, and we call that pi hat. Or we should say pi hat is defined in this case as y over n. The standard error of the estimator, which is used in the confidence interval calculation, it's also this estimated standard deviation of pi hat, is given as the standard error of pi hat square root pi hat times 1 minus pi hat divided by n. And finally, for the binomial test, we see that the relevant distribution that we need is the binomial distribution with parameters n and pi. So we'll now look at a binomial test and go through all the steps. Yeah, example 2 was about germination of seeds. We want to test in this case if the population proportion of seed that germinates is less than 0.9. Yeah, so that is the 0.9 is suggested by the salesman. They write it on the package maybe. So, and we suppose that 15 sample seeds germinated. So the phrase that we use, the population proportion is less than 0.9, is in the alternative hypothesis. Here we use the p-value method and pqrs to find it. Null hypothesis is about the parameter of interest, pi, and the null hypothesis says pi is 0.9. Alternative hypothesis, pi less than 0.9. Step 2 gives the test statistic, and we have seen that we can use as a test statistic y, the number of germinated seeds in the sample. Now, this also makes sense. This is what you would intuitively do. Look at how many seeds germinate. If 100% would germinate, you would say, well, pi will definitely not be less than 0.9. Or at least there is no evidence that that is the case. On the other hand, if no seeds germinate, then you would say, yes, there is clear evidence that pi is less than 0.9. So this number of germinated seeds in the sample is definitely an intuitively appealing statistic to look at. And indeed, we can use it here as the test statistic. Then step 3, and remember, steps 2 and 3 are just given to you. You don't have to invent them or so. Under the null hypothesis, y has a binomial distribution, n is given is 20, and under the null hypothesis, the pi is 0.9. Well, then this other steps follow as usual. Under HA is step 4. Under HA, y would tend to, well, where would it tend to? We see that pi is less than 0.9. Suppose it would only be 0.2. Then we would expect very few seeds to germinate. So under the HA, y would tend to smaller values. Yeah, first I should of course have shown the binomial distribution. Well, here you can see that, and you can also see that you would expect around 18 successes. 20 times 0.9 is the expected value. Under HA, y tends to smaller values, so we use the left-tailed p-value. Outcome, y is 15. We see that here in the graph. And now we can also find the left-tailed p-value. The left-tailed p-value for a discrete distribution is the probability that y is less than 0.011 or equal to 0.03, the outcome, and that is 15. So we find 0.011 plus 0.03 is 0.0432, less than 5%. So the null hypothesis is rejected. It is shown that in the population, the proportion of seed that germinates is less than 0.9. If we would use R output, we could use binom.test, 15 successes, n is 20, and the success proportion under the null hypothesis is 0.9, and our alternative is less. Number of successes is 15, number of trials is 20, the p-value 0.043, as we saw before. So this result completely is in line with the PQRS output. Then the second type of inference, confidence intervals. We remember that approximately pi hat has a normal distribution with mean pi and standard error or standard deviation square root pi times 1 minus pi over n. That means that if we want to make a 1 minus alpha two-sided confidence interval for pi, we can use the same structure as before. That is estimate plus minus a constant times standard error. Only we will use now a z value instead of a t value. And you can find these z values at the bottom line of table 2 in the book. The approximate 1 minus alpha confidence interval limits are pi hat estimate plus minus z value times standard error. It's an approximate interval, and the approximation is sort of thought of as good enough if both n times pi and n times 1 minus pi are at least 5. So that finishes the theoretical part for confidence intervals. We have one more issue to deal with, and that is the sample size. For making a 1 minus alpha confidence interval for pi with an error margin of at most e. Similar as the discussion in the previous lecture. For confidence interval, we have two precision criteria: the confidence level, or the 1 minus the confidence level, in this case alpha, and the error margin. The difference with situation 1 in last week's case with a continuous variable is that the sigma square in the formula that we had used at that time is now replaced by pi times 1 minus pi, which is the variance for one binary observation. The sample size formula n is equal to z squared times sigma squared over e squared, and that now becomes z squared times pi times 1 minus pi divided by e squared. Now if you look at the formula, you see something funny is going on. We want to make a confidence interval for pi with the data, but to do that we need to know what pi is. Well, in many cases there may already be some idea. For example, if pi is less than 0.2, then you could use, for example, 0.2 as a guess. The idea is that here we bring in a sort of guess, and if we have no idea at all, we could use pi is 0.5. Because pi times 1 minus pi can at maximum be 0.5 times 0.5, it's 0.25. But if pi is much smaller, this variance will also be much smaller, and then it could indicate that we don't need such a large sample size as when we would use 0.5 times 0.5. So only in case if you have no idea, then you can bring in pi as 0.5, and that gives us the largest possible n, so that is on the safe side. I mentioned before table 2 bottom line, where you can find the z value or the standard normal quantiles. Well, the t with infinite degrees of freedom is the same as the standard normal distribution. Another note, in the book you will not find z 0.2, which we sometimes use. It is equal to 0.84, and you can write it in your book as an extra value, so that if it would be needed in the exam, you don't have to go to table 1, but you can simply look it up here. An example about making a confidence interval. Yeah, it's on the proportion of binge drinkers at some large university. Yeah, it's an American example. I have been always shocked by the numbers, and I have no idea how realistic this is. But anyway, at this large university, we randomly select 500 students, and we ask them, did you engage or do you engage in binge drinking? And 240 said yes, and 260 said no. And now we would like to know, supposing that these are honest answers, which proportion of the student population at that university engages in binge drinking. Well, we have seen how this works. Let's first look at how the data collection is set up. Population of interest is the population of students at that university, and the sampling units are students from that university. The response X is binary. The student is a binge drinker or not. X is 1, X is 0. Yeah, so the response we gather from this is a binary variable. We take one sample. So from this we understand, we need to use the methods for situation 10. Yeah, and in the study guide you also see, for example, for a test, which test that would be, namely the binomial test. The confidence interval has its general structure, estimate plus minus a constant, and in this case times the standard error, and in this case the standard error and estimate are given by pi hat and square root pi hat times 1 minus pi hat over n. Yeah, so we can use this formula to find the confidence interval limits. Well, the estimate, 240 out of 500 said yes, so our estimate for pi is 0.48. The z value, z 0.025, because we wanted a 95% confidence interval, alpha divided by 2 is then 0.025. The value is 1.96, table 2 bottom line, or using PQRS, 2.5% on the right side, standard normal distribution, and we find the same value. Finally, the standard error, pi hat is 0.48, so we can calculate the standard error as 0.48 times 0.52 divided by 500, and that happens to be 0.022. So the standard error is 0.022. And then you know, roughly speaking, the error margin will be 0.022 times 2. Well, it's not exactly 2, but 1.96. Yeah, so the confidence interval has limits 0.48 plus minus 1.96 times 0.022, and that gives limits of 0.43 to 0.52. Yeah, so we're 95% confident that the true proportion of binge drinkers at that university is between these two values. Yeah, and as I said before, quite shocking. Then, how to calculate the number of observations required for a certain precision criterion. Suppose we wanted a 95% confidence interval with an expected width of 0.04. So the error margin should be 0.02 at most. Well, we used the last formula that we saw. N is z squared times pi times 1 minus pi divided by e squared. The z is 1.96, the e is 0.02, and the pi, yeah, we could simply use 50%. So let's start with the alpha. Z alpha divided by 2 is 1.96, pi is 0.5, or you could take a pi is 0.48 because we have already done this experiment. Makes very little for pi times 1 minus pi. So n is 1.96 times 0.25, and that is the 0.5 times 0.5, divided by 0.02 squared, and that is a very large number. We would need 2,400 observations. Yeah, so to get quite a precise estimate, 0.48 plus minus 0.02, we need this many observations. And why is that? Well, you could say in binary observations, there is very little information. So you need really many of them to get precise results. Okay. Yeah, the formula is again explained. Pi times 1 minus pi is this sigma x squared. Finally, output for the binomial test. Yeah, if you run binom.test, let's do it in this case, x is 240, n is 500, p is 0.1. Yeah, we are testing whether the proportion is 0.1. Well, then, of course, it's clearly not true. Alternative is two-sided. Yeah, we get a rejection. P-value is 2.2 times 10 to the power minus 16. This is the kind of smallest possible p-value that R generates. Yeah? So it's clear that we should reject. But in this case, I want to draw your attention to the 95% confidence interval, 0.435 to 0.525. Yeah, these values are somewhat different than the ones we calculated, and this is because binom.test gives a so-called Klopper-Pearson interval, which is not based on a z approximation, but on the exact binomial distribution. Yeah, and what it shows, what this means is that if we would have a success probability of 0.4354, and we would like to test whether this could be true, then we would find exactly a two-sided p-value of 0.05. Yeah, the one-tailed p-value is 0.025. Yeah, so for this, if we would test this probability, we would get exactly a p-value of 5%. So that's where this limit 0.4354 comes from. And likewise, if we would do the 0.5248, then the LPV would be exactly 0.025. So, overview for the one sample, one proportion case, situation 10. We have talked about the parameter of interest, pi, estimator, pi hat is y over n, and the standard error, approximate using the normal approximation. Yeah, the exact approach is using the binomial distribution for the number of sample successes. And you should be able to use PQRS to find probabilities. You should know what the expected value or the mean for y is, the number of sample successes given n, and the success probability, and also the variance and the standard deviation. Yeah, the binomial test is used for an exact test for one proportion. The confidence interval, we use the normal approximation, and the sample size calculations formula is given if the aim is to use the data to derive a confidence interval for a proportion or probability. Yeah, so that finishes part 1 of this lecture.